How good is laser scanning? It sounds like a pretty simple question. I think maybe a better question is how scary is laser scanning? That's actually the reason why I'm here is fear. I'm a land surveyor. I don't really have much to do with concrete. I've been a licensed land surveyor since 2010, kind of specialized in heavy construction, got involved in laser scanning in 2010. And so the reason why I'm here is because laser scanners have been used to beat a lot of concrete contractors over the head. I've been accused of doing some of the beating. That's not fair. I just report the facts, going out there trying to measure things and see what's going on. So I got involved with the 117 Tolerances Committee, and there's just been a lot of issues with scanning and costly repairs and different things. And so everybody wants to know, how good is the data? Can we rely on it? So I've been doing this stuff for quite a long time. I work for a large civil engineering firm in California, mostly in Northern California, the San Francisco Bay Area, and we do a lot of high-profile construction projects. So today I'm going to be talking about how good is laser scanning. We did a big study as part of the ASCC out in the Bay Area last October. So we're going to go over some of the results as that. We're going to talk about accuracy of a scanner. We're going to talk about what accuracy actually means. Can we rely on laser scanning, and the future of scanning, and what that's going to mean for concrete contractors, owners, et cetera, as far as meeting tolerances. So this article that was published, I was one of the authors, but I got to say thanks to Jim Klinger and Bruce Supernet. They both helped out quite a bit. I'm just one guy of a larger thing. There were about 30 people involved in putting this together, so it was quite an effort, and definitely thanks to all the participants and the co-authors as well. So it seems like a simple question. Is laser scanning accurate? And so the thing you'd think you'd do is you'd go look at a spec sheet. Like a lot of equipment, you know, if you want to know which car is faster, you can go to look at the horsepower numbers, or maybe a comparison in a Car and Driver magazine or something like that, right? Does anything like that exist for laser scanning? Do the manufacturers tell us how accurate their scanners are? Can we look at some industry publications? Talking to other users, well, what do? Well, unfortunately, laser scanning accuracy is very confusing and difficult. We have no standard. The manufacturers all state accuracy in different ways. We have 1 million different units. We have arc seconds and millimeters, and we have beam spread, and we have the color of the item. There's all these different factors that are involved. So you can't take a spec sheet from manufacturer A and compare it to a spec sheet from manufacturer B and C. If you do, they all make the greatest laser scanner ever, and they're all almost perfectly accurate. You see incredibly small numbers published, accuracies of things like fractions of millimeters, or, well, I guess decimals, like 0.5 millimeter or 0.2 millimeters, which makes things sound extremely accurate, but maybe they're giving a false sense of accuracy. So what does accuracy really mean? I think that's a really good question. I've got one definition here: the degree to which the result of a measurement, calculation, or specification conforms to the correct value or a standard. So when we talk about accuracy on a job site, we're not using dictionary definitions. What do we mean? Well, we think something's built the right way. We think a measurement is correct. We think we can rely on that information or that measurement. That's kind of a working definition of accuracy. So I love these charts. Everybody makes different ones. The difference between precision and accuracy. Probably all of you guys have already seen this before, so I won't spend a lot of time on it, but I think it's worth talking about. So here we have a bullseye, and we're trying to see the difference between precision and accuracy. So we have two axes there. So if we look in box A, we're seeing measurements that are neither precise nor accurate. So precision being the measurements themselves being consistent with each other, and accuracy is hitting the bullseye, right? So box A is exactly what we don't want. Box B, we've got some accuracy, but we don't have precision. So we're to that bullseye, but the measurements aren't grouped very close together. They're kind of all over the place. Box C has the opposite problem. Lots of precision. All the measurements are very repeatable, but they're completely missing the target. And I kind of like to use that as an example of the difference between what laser scanning, the different aspects of it. So the equipment that is manufactured is actually, it's very precise. Surveying has been around for a long time. And for a long time, I think a lot of people think of surveyors as measurement experts. That's what we were. We were able to use these fancy equipment and calculations and be able to do magic. We could walk out in the middle of a field and tell you where the new building goes. And how do you do that? Well, it's math. It's not that hard. It's minimizing error. So the manufacturers of the equipment have gotten very, very good at this. If I set up a laser scanner and tell it to go scan that wall from the same position, and I scan 1,000 times, I'm probably going to have a variance in that one spot of maybe a millimeter or two. So the precision is awesome, but there's all these other things that go into effect, other sources of error, and that's where we get into needing the accuracy. So box D, that's what we're all looking for, and that's what people expect. You buy a very expensive piece of equipment, you go out and you produce these crazy, pretty deliverables, these heat maps that seem to drive people crazy. So much data is captured, and there's so many claims about accuracy that people have a tendency to rely on it. So what is actually most likely a box C product is being represented as being box D. And so that's what we're trying to figure out. And without getting into a ton of statistics, I'm actually a college dropout. I didn't even finish my statistics class, so I'm not going to lie. But I do work with numbers a lot. I work with measurements a lot. So we're going to talk about a 95% confidence interval. That's kind of the standard when you're talking about accuracy. And so that means basically, I'm sorry if I'm butchering this, but if you're going to take 100 measurements, you've specified what your confidence interval is, the accuracy at 95%. That means 95% of the measurements are going to fall within that range. So if I say my measurements are accurate to plus or minus 1/8 of an inch, if I measure 100 times, 95% of those measurements are going to be within 1/8 of an inch of the true result. So when we're talking about how good is laser scanning accurate, we need to understand what we're talking about. And then we have to get into further some terms that are really important to the work that we're doing. Those terms are repeatability and reproducibility. So I actually think this is one of the most important things about land surveying. So my profession, it's been interesting. The equipment has gotten so easy that everybody's using it now. And so I go out to a job site, and a lot of work that was traditionally performed just by surveyors is being performed by everybody. So I have clients here that used to hire me that don't anymore because they self-perform. They have their own total stations. And that's fine, but one of the keys to good measurements and good surveying is repeatability and reproducibility. So repeatability is, can the same operator using the same hardware and processing recreate the same results? So can you get the same measurements? If I come out and measure today, that point over there that I'm talking about, and I come out and measure it tomorrow, am I going to get the same results? Do I have a system of minimizing error? How is my technique, and how repeatable is my measurements? So that's important. But what we're talking about, I think, and what's really important in the industry as far as laser scanning is reproducibility. And so that is, I can reproduce my own measurements, but can someone else that has not talked to me get the same results? And that's really important. So if this equipment and process is reliable, what should happen is I should be able to come out and do my measurements and prepare an exhibit, and then someone else using a laser scanner can come out on a different day without talking to me at all and be able to get similar results. And so that is what we were trying to test. And then one last thing that we need to talk about too. So we're talking about ACI 117 committee tolerances, because that's what this is all about. Tolerances cost money. They cost money for the owner because if you specify a tighter tolerance, then the work is going to be more expensive, and contractors having to. So that's why tolerances are so important, and I really appreciate the work that ACI is doing with this. I'd like to see more of our industry do something similar. So when we're talking about tolerances, we have to get into this test uncertainty ratio. What that means is, looking at this little graphic here, I realize I can't point anything with my mouse, you have a plus and a minus tolerance. And part of that tolerance is going to be taken up by the measurement accuracy. And so according to a lot of standards agencies, they like a test uncertainty ratio to be 4-to-1. We're actually working on publishing a paper as part of 117 that talks about this test uncertainty ratio. This is most likely what's going to be used. And so that's what we used when we were conducting our experiment here to see how repeatable and reproducible laser scanning was. So a test uncertainty ratio of 4-to-1 means you have to have an accuracy at least of the tolerance. So if I have a 1/2 inch tolerance, that means my measurement has to be 1/8 of an inch. And that makes sense, right? If I'm going to go try to measure if something's within a plus or minus 6 inches, I wouldn't want to take out a tape measure that only had 1 foot marks. There'd be no way to accurately do that. So we have to have a somewhat reliable measurement to be able to do this. So now that we've kind of gone over some of the vocabulary, let's get to the heart of this. This study that we did, what we did, and what the results of it are. So in Walnut Creek, California, which is in the San Francisco Bay Area, we had an owner that was gracious enough to let us go out there and spend a weekend bothering their construction site. They had their superintendents and people out there making sure that we were safe. We had 2 different slabs. One was a slab on grade. One was an elevated podium. The podium slab was going to be post-tension, but it had not been tensioned yet. Both the slabs had cured, and got 8 different participants to come out. We had a mixture of people. I'm a surveyor. We had a couple of surveyors. We had some laser scanning service providers. We had some contractors, and we actually had some manufacturers' representatives out as well. So we had a good cross-section of people. We had, I believe it was 3 different manufacturers represented out there. So we didn't get everybody, but we got a good cross-section of the industry. And then we were going for repeatability as well. So we actually had everybody work Saturday and Sunday. So on Saturday, they scanned the slabs, and on Sunday, they scanned the slabs, so that we were able to see if they could reproduce their own results. And then we also had them, on one of the slabs, we set them out with a direction on what we were doing. We actually did some F-number testing as well, which we're not going to get into today. That's going to be a future article that's going to be coming out soon. We're working on that right now. But this was just, we provided some coordinates, some XYZ coordinates of some known points, and then we installed some unknown points. Just black and white targets were installed, and then so we provided coordinates on some, and then we had them return the data to us on 10 other additional points. So we had them give us, they went out, collected their field work, processed the data, combined it together, and then created the deliverable, which was the FF and FL numbers as well as the coordinates. So that's kind of what we did, and I don't know how readable that is on the screen, but this is just an example. This is a table. By the way, all this is in the article from Concrete International that was published last January. So if you want to read more in detail on what we did, that article is available on the website. You can take a look, and there's a lot more data tables. I could spend hours talking about this, but I just kind of wanted to give a high level of what we're doing and why today. So this is just one table. This is the ground level slab, and so we're looking at participants A through H. We randomized these so that nobody knew who anybody else was, and then we have the minimum, average, maximum, and standard deviation of the measurements for X and Y, so the horizontal axes, and then for the vertical axis, Z. So that's the way coordinates are used out on the job site. You have the X and the Y, and then the Z's going up and down. And so those are treated separately. And so you're seeing here is, unfortunately, quite a bit of variance. It's a lot more than we expected. So some providers were able to get very close to the surveyed coordinates of these targets, and some were not. So we saw quite a bit of spread. We're seeing standard deviations of, up to almost or beyond even 1/8 of an inch. And so applying the tolerance uncertainty ratio means a lot of those tolerances that we're seeing in ACI 117, maybe it's not appropriate to use scanning for that. But there is some hope. There is some hope. This is another table. And so what we did here is we took, these are the kind of the statistical analysis of all the measurements put together. But we noticed that the 3 of the 8 were able to get very, very consistent results. So looking at that bottom, 8 times U, which is 8 times the standard deviation, we're seeing what we were able to get here. And if you look at the 8 participants together, and then you take the 3 participants with the lowest errors, those errors are almost half. So somehow, workflow, process, something caused 3 of these participants to be able to get more consistent measurements. And we didn't see any kind of correlation between manufacturers or type of client. So we're thinking that, I mean, there's going to be further research and testing that needs to be done, but our initial conclusion is that, hey, maybe there's something to this. Maybe there's some best practices that can be implemented to kind of reduce these errors. But based on what we saw, I mean, this was kind of the summary of the article, and this is why I've now lost friends in the laser scanning business the same way I lost friends in the concrete business. Based on this, applying that 4-to-1 tolerance uncertainty ratio, we're saying that laser scanning shouldn't be used for vertical tolerance of less than 5/8 of an inch and a horizontal tolerance of 1 inch. And so if you've looked through those ACI 117 tolerances at all, that's going to cut out a lot of the work that's done. Plumbness of a wall is going to be better than that. I mean, forget doing stairs or ADA ramps. Those tolerances aren't even close. So what do we do? Laser scanning is not going away. Laser scans are going to be used. Contractors are going to be shown these big heat maps, and money is going to change hands or not based on the results of these surveys. Well, one thing that ACI is doing, there's actually a joint ACI-ASCC. We're working on a laser scanning best practice guide. So the subcommittee of 117 is actually producing this. We've applied and got approved to put a paper through TAC. We are about halfway through getting the draft done. The first 6 chapters are drafted up. So that's going back to the laser scanning committee for editing right now. We're hoping to kind of get the rest of the chapters drafted to the full committee next year is the goal. It's quite a bit of effort, but obviously there are techniques that make a difference. And so that's the point of this. This technology is not going to go away, so we're trying to mitigate it and make sure it's being used properly. Also, I think this is an important point. Specification compliance and quality control are not the same thing. Laser scanning is not useless. If we're going to be trying to evaluate specifications, maybe it's not the best tool for that, but I don't think we need to throw laser scanning away. Many contractors, owners, general contractors, guys like me, we're out using laser scanners, and I can tell you in my practice, I'm a licensed land surveyor, and I sign and stamp laser scanning documents almost every day. So I'm not putting my license on the line by putting out a shoddy product. I just think we've developed techniques and error mitigation methods that are doing us to get reliable results. And I think one of the key things to do that is my first boss told me, if you're not checking, you're not surveying. So there's always a way to check what you're doing. And so we always use multiple methods to do verification. And I think that's something that needs to be applied in the best practices process. How good is your data? Well, you can't answer that question unless you do some independent checking. And so we use a similar process internally at our firm where we use provided coordinates that we generate externally using other survey equipment, but we don't use all of those in our solution. And so when we're georeferencing or putting laser scanning data together, we have points that we use to do that, and then we have this other pool of points that we can do an error analysis on and be able to verify how accurate our work is. And that's why I'm willing to put my neck out on those deliverables. I think a discussion also needs to be had about how accurate is accurate enough. A lot of these 117 and the 117.10 document were developed long before laser scanning was something that actually existed. And so now we may be, back in the day, if we were going to measure this wall, we would have done it on a 10-foot grid. Now I can easily, in minutes, measure it every 1/8 of an inch. So if 90% of that wall is complying with the tolerance, is that enough? Is 80%? Is 100%? Well, we don't know. That's going to take some further testing and some thoughts on what we're going to do with these tolerances as time moves forward. Technology is moving forward, and maybe a more statistical method is what we need to incorporate. And also, there's some tolerances that maybe aren't fair. That's something that needs to be evaluated as well. If we can't effectively measure the tolerance, then what good is the tolerance anyway? We have a tolerance, I think, for stair tread height that's a 32nd of an inch. I just don't, if I sent out 50 people to go test that tools, we're not going to get a tolerance uncertainty ratio small enough to make that be justified. So where does that come from, and what can we do about it? And then also, as I mentioned, we're going to be publishing another paper on the F number testing for floor flatness, the FF and FL. It was very interesting as well. So I'm sure we're going to get some interesting comments after that comes out, just like we had on this article. So that's all I had. Does anybody have any questions? Thank you.